Hi everyone. So this video is going to be about our rocket launch lab. Oh wow, I just spelled the word launch wrong. LOL. Okay, let me fix that for us. Launch lab. Okay, this is going to be for your calculations. Let's see. If you did not get a time from your video of the time of flight, and time of flight refers to the moment it takes off to when it hits the ground, you are actually going to end up using one of these times. You could either say T is 6 seconds, 7 seconds, or 8 seconds. So again, you're going to choose one of these. Okay. Your first calculation, what is the time at your max height? Okay, how we actually go to figure this out? Well, it takes, when the rocket is launching to get here, and then when it comes back down, it takes 1/2 of the time, 1/2 of the time. So in order to get that, we're going to divide the time by 2. So your equation will be T at max height. And this is just me being very specific, like it's just T, right? Just regular time. But I'm saying time at this particular point. So T at the max height is going to be total time divided by 2. And again, this is your total time up here. So you're going to take one of these numbers, unless you have the video and you're going to use your data. But if you don't, and you just want to get this lab over with, you are going to use one of these 3 times that I've already selected for you. Once you do that, right, you're going to substitute, you're going to say time at max height equals, I don't know, let's say for example, again, this is just my example, so, you know, I'm going to make the time just in my example 9 seconds, just to be different. Okay, so then I would say T at max height, is equal to 4.5, not meters, 4.5 seconds. My second calculation would be what's the VI, right? The takeoff velocity. So when it moves up, we know when it's up here, VF is equal to 0 meters per second. We know that acceleration on Earth is negative 9.8 meters per second squared. So I would use VF equals VI plus AT, because now I also have the time. I'm going to take whatever this is. So you have to do these in chronological order. Okay, so you're going to substitute with units, right? I'm just going to write here with units to find this thing. Then the third part is finding what is the height. Okay, so whatever you use in, or whatever you calculate in part 2 is going to be what you use in part 3. So you have 2 different choices. D equals VIT plus 1/2 AT squared, or you could use VF squared equals VI squared plus 2 AD. Again, just to recall, you're using T at max height in this equation, and you're using the VI that you've calculated. So this is from part 1, and this is from part 2. Okay, so again, you're using previous information, and then when it says, what is the total distance? Again, that's your rocket going up and then coming back down. So this first trip is its first height, D1, and then when it comes back down to Earth, right, that's D2. So in order to find that, you could either take D total, right, this would be your equation, D total equals D max height. Again, I'm just being specific. You could just write D times 2, or you could say D total is equal to D1 plus D2. Okay, so those are the 4 calculations that I have to see. Again, make sure everything has an equation and units. Because I will be taking points off. And then in terms of the questions, the first question is going to ask, like, what's the deal with the magnitude and direction of acceleration at max height? Let's think about in all of our equations that we've used, what was the value of the acceleration that we've used? Have we ever referred to it as being any other direction or any other number other than 9.8 and specifically negative on planet Earth? Okay. The second one's going to ask about what happens to the velocity. So as this object is going up, we know up here VF is equal to 0. So what does that mean when it's moving upwards? And then what does that mean when the object comes back down to Earth? So talk about when it goes up, talk about it when it comes back down. And then the third question is like, how does air resistance play a role? We kind of spoke about this when we were talking about the parabolas, right? That's a perfect parabola where there's no air resistance. But when there's air resistance, that's what a projectile's trajectory looks like. So you tell me what exactly about the second parabola I drew in black, how does it differ from the first one? And then the fourth one is going to ask you to kind of say what improvements or modifications would you make if you were to do this again? And then it asks to kind of discuss about like what do the other classes use. So I'll give you an example. So for the other classes, their time of flight range from 4 to 6 seconds. I think it said 4 seconds was another class had 10 seconds. So these were their times, but they all used roughly this much, water in their thing. And for the most part, everyone was between like 50 through 60 PSI. This one was, I think, 40 to 60 PSI. And the last one is at 60 PSI. So if you want to compare the other classes compared to what you did, you can also do that too. Okay, so hopefully that helps complete the lab. All you have to do is complete this on loose leaf and turn in your loose leaf to me by at least Wednesday, and then you're good to go.